All right. I was going to talk some about chapters 4 and 5, unless there are other questions at the moment.
We're not doing labs here.
No, it's sort of in a sense, a group lab. I'm not giving you the formality. Well, actually, now that you bring it up, we're not doing the formal lab on this, but what I'm about to do here is actually a lab in the 16-week course that you would have done.
Oh,
However, I did post a lab, an online lab. I posted it today, and that's something you will not have class time working on that. If you have questions, ask, but it is posted. There's a simulation site where you can go to it, and so there is a lab officially that you were assigned today, and it's due in a week.
it's the Becker lab, right?
Yes, that's the one. If you go on to it's in the lab course and not under this class. So if you go in the lab course and you can't see it, let me know. One other warning is that last fall, spring, I think it was in the fall, I posted it, and it was a purely online class. It was a lab they were supposed to do. And I got a question from a student saying, what am I supposed to do in problem number 2? And I said, well, pretty much the same thing you did in problem number 1. And there was some back and forth, and I was really confused about what the student was asking. And it turns out that what I posted, it took the picture that was basically the basis for problem number 2, and it decided it wasn't actually going to show it. And there are various other things that shifted around. So what I posted this morning had all the pictures that were supposed to be there. When I brought up the previous version of the lab, they weren't all there. So I'm not quite sure what happens. Sometimes the computer says, you know what, I know you thought you wanted to put this picture here, but we really know that you don't want it there, and it took it out. Or it expanded it, and you only saw this part of it. So if it looks like something's missing, just let me know, and then we'll go from there. All right, other questions at the moment? I believe so. Let's go with yes.
Yes.
I said I believe so.
Okay.
I know there's some people who have special situations, and so I've dealt with individuals.
Okay.
If you have special circumstance, I'll be glad to talk to you about that. But by end of day.
The linear motion lab.
We didn't finish that one. The one that we did on the last Wednesday.
Oh, what did I say last Wednesday?
Think over it.
Yeah.
Maybe it would make,
Did you think over it?
thought of a lot. I feel like my brain's gonna explode.
Okay. But your brain didn't explode. That's the important
right.
thing. All right, so what I plan to do today was not going to take, I don't think it's going to take the full hour and 50 minutes or hour and whatever we have left. So if I start to talk about momentum, stop me, because that means I forgot that I would potentially give you time at the end.
Okay.
Yes?
So, how long do you stay in this classroom so that we can turn work in later?
All right, so on Mondays and Wednesdays, I'm here till at least 3 o'clock. If a student's working in the lab, I'm sticking around till they're done, usually. If you are on campus, if you just need to go finish doing the work and then bring it back, you can always slip it under my door, my office door.
What door is it?
if you go down this hallway, there's another classroom right on the other side of this wall, and then just past that classroom, there's a small little alley. And there's a mechanical room at the very end, and my office is just before that. It's got a Ukrainian flag on the door and my name right outside it.
Okay.
And you just slip it under there. If somehow you're, there's too much there and you're trying to think, I can't find it. I've been in that situation, trying to find people's houses sometimes. If you slip it under the door of the lab, it will get to me.
Okay.
Probably an email saying, hey, I slipped it under room, I think it's 306. All right, other questions right now? We've talked about forces, chapter 2. We've talked about acceleration in chapter 3. Let's bring them together. In what I consider, probably in the video too, the most important equation in all of physics. This is actually the first real physics equation we're dealing with. All that stuff in chapter 3 is math definitions. If the math people define it differently, then chapter 3 would have been different. But this one cannot be derived at all. It's not based on definitions. This is based on experimental evidence. So, the simple case, I got a 6 kilogram mass here. I push on it with a 3 Newton force to the right. If I want to know what is the acceleration, well, it's plug and chug. I know that's my force. How do I know that's my force? What's the big clue? Yep. So I have 3 newtons. Now I need to somehow indicate direction because it is a vector after all. And so let's just make it easy and I'll just say it's pushing in the positive direction. So I'm going to establish my convention. So positive 3 newtons is equal to my mass. And how do you know that's my mass? Times acceleration. Nope, wrong place. Down there. So the math problem I'm dealing with is 3 is equal to 6a. That's the math problem. How do I solve for a?
Divide by 6.
Yep, I'm trying to get a by itself, so I need to get this over, so divide by 6. And so a is equal to 3/6 or 1/2 or 0.5 or however you want to express that. And units?
Meters per second. Squared.
And once again, that's a class, we got it. Now occasionally, I'll have a student do the units a little bit differently. If you track the units as you go through this, now we're basically here, you divide by 6 kilograms. And so the math piece is 3 divided by 6.
So that's 6, that's 61 grams or 6 kilograms?
That's 6 kilograms.
Okay, I'm not confused now, sorry.
Any other issues with my handwriting? Anyone else want to insult my handwriting?
Sorry.
No need to apologize. Sorry about that. Yes, Kimberly.
So the answer would be 0.5. And what's the answer?
So 0.5 meters per second squared.
Oh, okay.
I'm about to show an alternate answer, which is also equally correct. All right, so I divide by the 6 and the kilogram, they both go away. And now I'm left with 3/6, which is 0.5, and units of newtons per kilogram. That's also a correct answer. Either one is correct. Because the powers that be said that a Newton is, by definition, I'm pretty sure I've done this with this group before. Maybe it was the other group. A Newton, by definition, is a kilogram meter per second squared. And so if you divide by kilograms, you get newtons over kilograms here, and just left with meters per second squared over here. Notice also, the first time I went through this, I didn't bother writing units down here, because I know I'm finding acceleration. I'm working in what I generally refer to as the NICE units, or formally, I'm working in SI units, or International Standard Units. I'm working with kilograms and working with newtons. Acceleration is going to be meters per second squared. If I throw in a problem which had you find the velocity or speed, it's going to be in meters per second, just because I'm dealing with the standards. Okay, change your mind. Now let's make it a little more complicated. 3 Newton force pushes on a 6 kilogram object of the box eastward. If the box starts at rest, probably should throw in one other thing here, eastward, across a frictionless floor, frictionless horizontal. If the box starts at rest, how far has it gone after 4 seconds?
Did you use x equals v times t? Are we doing something totally different?
Nope. If you can figure out what V is, or what is.
0 and 6. No, wait, no, 0 and 4, I'm sorry. No, that's wrong. What am I doing? I don't know, what is 0?
All right. Anyone else? Yes, Isabella?
Can we plug in 3 newtons equals m times 0.5 newtons per kilogram and solve for m?
Except I've given that to you. Sorry to spoil that. I told you the math right there.
Oh, never mind. I was thinking about meters. I don't know why.
Yep. Technically, if I hadn't done this first part here, you would be using that equation absolutely to find acceleration, but we've already done that. All right, so let's sort of take this step by step. I'm just going to say eastward is that way. I'll make it positive and call that eastward. Traditional map. I have a force being applied to this box. It's on a frictionless floor, and it's just going to be moving horizontally. Frictionless is because I don't want to have to worry about friction forces slowing it down. Horizontal is I don't want to have to worry about, it's being on a slope and wanting to automatically slide one way or the other. I'm just simplifying it. Frictionless horizontal floor means I'm only worried about this 3 Newton force. Here's my problem right there. I got a box on the horizontal floor, 3 Newtons pushing that way.
only three?
It depends on what you mean by that.
Like, you said, what is velocity?
So it starts out at 0 meters per second,
Right.
and you're saying it gets up to 3 meters per second?
No.
We'll get there. All right, so here's the situation. So generally when you're given a word problem, I would recommend drawing it if you need to. If you can picture it completely in your head, that's great. And if you can't, let's draw it. If I do the force diagram, what are the forces acting on the box?
Three meters to the right.
I heard weight.
Down on the box.
Yep.
Up on the ground. Normal force.
Pushing which way? Or onward? Up, okay, so I got a normal force up. And I think somebody said it.
To the right. What, eastward?
Say it again, Hannah.
Eastward onto the box.
Yeah, and specifically 3 newtons. This would be a case of an other, because I just say there's a force there, it's given in the problem. I don't tell you what's causing that force, but there's 3 newtons pushing that way. All right, so there's our force diagram. There's no friction because I said the ground was frictionless. The weight and the normal force are going to cancel each other out. This box is not coming off the ground or digging into the ground, so the net force is just this 3 newtons, which is exactly what we had just done. First, I'd find acceleration. So 3 is equal to 6a. A is equal to 0.5 meters per second squared. The next bit. There are 2 approaches, so I'm going to do a slightly longer approach first, and then I'll do the shortcut. I got time. I have velocity. This is in meters per second. This is in seconds. And the problem lasts till second number 4, 2, 3, 4. My velocity starts at 0. And after 1 second, how fast is it going?
One meter. Second squared.
0.5.
It's not going 1 meter per second after a second.
Oh.
You said 25?
No,
0.5, yes, 0.5. Because the acceleration, this is the same as 0.5 meters per second. So after every second that passes, my velocity changes by 0.5 meters per second. So after 1 second, it's going 0.5. After 2, after 3, and after 4. If I want to know how far it went, well, what's my average velocity? That would say sad brace. Better. What is my average velocity for this 4 seconds?
1.
How'd you get that?
2 minus 0 divided by 2.
Ooh. What you said was off, but there was also a mistake in there.
What's the average velocity?
1.25?
I know the mistake that you made.
Okay.
How many numbers did you add together?
You have to add 5.
Going down to 0, so only counted at 4 instead of 5.
Yep, that's the common mistake right there. All right, so one way of doing the average is I got 5 numbers here. I add up all 5 numbers and divide by 5, and you get
1.
that's my average right there. You could also have done it the shortcut. Acceleration is constant. So you could have just averaged the first and the last one. So 0 plus 2. I think the first person I heard speak said 2 minus 0 divided by 2. Actually, I think I heard 2 minus 0 divided by 0, but I might have misheard. So you can add up all 5 numbers and divide by 5, or just add the first and the last one and divide by 2. All right, so my average is 1 meter per second. Yes, Kimberly.
You can only add up the first and the last one if it's constant.
If acceleration is constant, yes. And I know acceleration is constant because it's implied in the problem, but the fact that the force doesn't change, that implies, that not only implies, that means the acceleration is constant, if the total force is constant. All right, so I got 1 meter per second for 4 seconds.
4
Oh.
meters.
Yes. So displacement is acceleration times, oops, try that one again, is average velocity times time. So that's 1 meter per second times 4 seconds, which is 4 meters. Now, we do have another way of solving it. Since we've satisfied, since it starts at rest and acceleration is constant, we could use that equation that Hewitt had, modifying it slightly more generally. If it starts at rest and acceleration is constant, we can also use this equation. We used it once before, except acceleration was the acceleration due to gravity, g, so the equation was written slightly differently. But this would be 1/2 times 0.5 times 4 squared, which is 4. And again, the simpler one is whichever way your mind is working at the moment that you have to do it. There's some people there with looks on and furrowed brows, like you want to ask a question.